All right. Guess we can go ahead and get started here as people are filling in. Hey there, Jan. All right. So this is the Rook project intro. My name is Jared Watts. I'm one of the maintainers on the Rook project. And Rook was recently accepted a couple of months ago as a hosted project by the Cloud Native Computing Foundation, the CNCF. So that's why we're talking about it today. So just a quick show of hands, who has actually used Rook so far? Good. Cool, fair amount of you guys. So let's talk about what Rook is. So Rook is a cloud-native storage orchestrator. And so what that means is that in cloud-native environments, you can use Rook to deploy, manage, set up, configure all different types of storage solutions. So, inside Kubernetes, you can use it to deploy, let's say, Ceph or Minio or some other storage solutions into cloud-native environments. So how it does that is by extending Kubernetes with custom types and controllers that we call operators, and we'll get into that more. And some of the interesting things that it does, kind of the value that it's bringing here to your storage needs are a bunch of automation. For deploying and bootstrapping, configuring, scaling it up, scaling it down, upgrading your cluster, disaster recovery, all that sort of stuff. Complicated management tasks that you need to complete in your cluster, it'll perform those for you. And as we kind of alluded to earlier, it's now a framework as well for other storage providers and solutions to integrate in with Kubernetes as well. So Rook is an open source project with the Apache 2.0 license. And as I mentioned, it's hosted by the Cloud Native Computing Foundation now, as of the end of January, I believe. So let's talk about storage in Kubernetes and what a normal solution or deployment looks like there. So oftentimes with Kubernetes, you have your applications that are running inside the cluster, but you have, for those applications storage, what happens often is that you will have an external storage setup. That could be running, something like an Amazon with EBS or a Google persistent disk, or it could be an appliance, in a rack somewhere in your data center. Either way, though, that storage is coming from somewhere external to the cluster. So there's a couple of limitations with that approach. One thing, the big kind of overarching aspect is that it's not portable. So when you have your application and it's got storage needs, if you're relying on storage that's kind of external in the cluster somewhere, you need those to be accessible when you're deploying your cluster. So that creates a burden for deployment of if you want to pick up your application, take it somewhere else and put it into another environment, say to move from Amazon to Google, you're going to have to also worry about how the external storage gets moved over there as well. Another thing is if you're relying on storage from, let's say, a cloud provider, you're going to often end up worrying about lock-in with being in a cloud provider service and relying on something like Amazon's relational database service, RDS. You take a dependency on that from your application, and it makes it more difficult to move your application somewhere else. So one approach to this, solving this, is making storage run on top of Kubernetes also. So we already have a Kubernetes cluster up and running. You've got your applications running in Kubernetes. So we could also use Kubernetes to manage your storage as well, in addition to your application. So this then allows us to have highly portable applications because we're not only describing the application itself when we're deploying it, we're also describing its storage dependencies as well. So you have a situation where your application itself can be described, by way in a set of Kubernetes resources, pods, services, things like that. But you can also now start describing your storage as well, and hand in hand, those can get deployed out to any environment that Kubernetes runs in, and be very portable that way. So you can, you can deploy it to Microsoft Azure or to Amazon or to, DigitalOcean, wherever it may be, very, very easily. And this is also not the only architecture that you can, enable this with. You can also have a dedicated Kubernetes storage cluster by itself that's running your storage to kind of separate your compute from your storage. So let's talk about abstractions real quick. So that's one of the ways that Kubernetes accomplishes being able to run everywhere, is by having a strong set of abstractions that are applicable to all environments that they run in. So for instance, a pod is a pod no matter where it's running, right? It could be running on-premise, it could be running in Amazon, doesn't matter. A pod captures the concept of an application running in an environment. So similarly, we need some portable abstractions that also describe data needs. Your application needs a database, or it needs a message queue, whatever it may be. Your application has needs of data, if it's going to be stateful, if it's going to be useful, right? So we want to make some abstractions for those as well, for data that's going to work across environments, across providers, hybrid scenarios, on-premise, cloud providers, all that sort of stuff. And then we get into this example here of when your app needs a database. If we have an abstract concept for a database, then when you go deploy your app inside Amazon, it can use RDS, and if you deploy your app within Google, then it will use Cloud SQL instead. So basically, this is making your app portable, and the advantage of that is that you get to choose the best environment for your code to run in. You can choose the best cost, or the features that you need, or resiliency, or even compliance. If one particular cloud provider has a data hosting policy that works for your country, or the compliance for your country, then you'd have to pick them. And you've defined your application in a way such that it is portable now, and you can easily choose where you want to deploy it. So let's talk about how Rook does this. It works on a couple different ways to extend Kubernetes and leverage the power of Kubernetes. One is the operator pattern. We know of a number of operators out there now. Prometheus has one, etcd has one, and Rook also has an operator, or set of operators actually. So real quick, we'll just talk about what that is. So operators basically codify their expertise or subject matter expertise for how to run a complicated piece of software. So, running software, especially distributed systems, they have a lot of complexity. They've got a lot of, components to them. And there's a lot of tasks that you need to do in order to keep that running healthy and running, up. So an operator is a Kubernetes piece of software that automates that for you. And the way it does that is by running a control loop, just like any of the other Kubernetes controllers, the node controller, pod controller, admission controller, all those things. They basically run in a loop that does three things. It first observes the state of the cluster right now as it is, and then it analyzes to determine what differences there are in the cluster now and where we want to be based on the user's desired state. And then it performs operations with the Kubernetes API to manipulate the cluster and to make sure that it ends up being what the user wants. And then the other thing that Rook uses and many other projects use as well to extend Kubernetes is something called custom resource definitions, or CRDs. So these are the way that you teach Kubernetes about new objects. So in the Kubernetes API, you've got the built-in objects, pods and services and config maps and things like that. But with the CRD, you can declare arbitrary types, any type that you want. And then once you've defined that type, it looks just like any other object in the Kubernetes API, and you can even use kubectl to manage it as well. So in a CRD, that's you can have all these different properties defined for how a user might want their system to act. So the user can create one of your custom resource definitions and set the different properties that they want in order to get their system configured the way they want it to. All right, so as we talked about, Rook has a number of operators that are implemented to enable distributed storage systems and other types of storage to now run inside of Kubernetes. They capture the desired state, like we were talking about, for a storage cluster. So for example, Ceph is a distributed storage system, and it's got a lot of moving parts. It's got a lot of complexity. But the Rook operator and the Rook custom types have captured some of that into more abstract concepts like a cluster or a pool or object store. And so the user can create those, and the Rook operator will be watching for those, see what the user wants, the desired state. Oh, they want a new object store, or they want a cluster with this amount of storage. And then the Rook operator, on behalf of the user and their desired state, will make that a reality within Kubernetes. So as we talked about also, some of the really more interesting things that an operator can do is some of those complicated things that a human normally has to do, such as handling upgrades or rebalancing the cluster. Those are complicated tasks. There's a lot of steps along the way. There's a lot of checks you need to make sure that everything's still healthy, possibly even roll back the cluster if something's gone wrong. And that's, that could be complicated, but having a piece of software to do that for you, an operator that has that codified logic to do it for you, makes your life a lot easier when you want to, create a cluster, manage a cluster, upgrade a cluster, all that sort of stuff. One really interesting, or one key point here, is that the operators that Rook provides to manage different storage types, they're not on the data path. The storage systems, they're the ones that handle the reads and writes to disk, but Rook is more of a management aspect of that to make sure that they deploy successfully, that they're kept alive, healthily performing management tasks. So Rook, these operators are not on the data path. And that ends up being pretty good because if you look at a piece of software like Ceph, which has been in development for years and years to reach the level of maturity and reliability that it's obtained now. We don't want to be in the business of writing a new data path, basically. We want to take advantage of some of those existing storage systems that have been out there for a while. So this is a slide just about the architecture of Rook, kind of putting a little bit of a visualization to everything that we've been talking about so far. So on the left, we'll start at the left. And so using kubectl, you can manipulate objects such as clusters, storage pools, object stores, things we talked about before. And so as a user, when you're using kubectl, you're creating instances of those objects that go to the Kubernetes API. And in the Kubernetes API, they'll get stored there, and there'll be events for them, such as the user created a new cluster. And now we see in the top right that this is where the operators are watching. They're getting an event from the Kubernetes API that says that new cluster was created, and then it goes out and does the right things in the cluster to make sure that the request from the user for new storage or a new storage cluster has been created, and it's persisted, and it's healthy, and all those sorts of things. If we look at the bottom right of the image here, we see that there's also a volume plugin that talks to the kubelet when there's a dynamic request for storage. So, for instance, if a new pod comes up that needs a block device, that goes through a dynamic provisioning flow that is a common thing in Kubernetes. But eventually the request gets routed over to the kubelet that's running on the node where the pod will be running that needs that storage. And the Rook plugin there will make sure that the storage gets mounted and prepared for the pod to start consuming it. And just a quick example to kind of tie a few things together here. So when we're talking about Ceph running on Kubernetes, what the user does is creates an instance of one of those cluster CRDs, right, a cluster type. So we can see here on the left that this will be a YAML file that a user will use kubectl create -f and pointing to that file there that specifies how they want their Ceph storage cluster to get created. They can specify things like what devices to use, where metadata should go, the networking information, whether to use the pod overlay network or to use the host network. And on the right, we see a little visualization of the various components of Ceph that have gotten placed and scheduled around the cluster by the Rook operator. And at the end of it, we have a functioning distributed storage system that's been deployed within our Kubernetes cluster and can now be managed by the operators and various Kubernetes constructs. So that's Ceph, but we also have support, new support, for other types of storage within Kubernetes. So from the work that we did with Ceph, we learned a lot of lessons and saw that there's a lot of patterns that can be applied to other types of storage systems as well. So now you can think of Rook as not just a collection of operators and CRDs, custom types. It's also a framework that can be used for other storage providers that want to integrate into Kubernetes as well. Some of the patterns there that you see are normalization of how you declare and define storage resources of, oh, I want this disk or this directory, or this is how I want data to be provisioned, or I want compute and storage to be separate. Those types of decisions that you need to make when you are defining how your storage cluster should be created is now a normalized, consistent way across more than just one storage provider, more than just Ceph. Operators, they're complicated pieces of machinery, but not that complicated. And the Rook framework here has a number of patterns and the plumbing for a storage provider that wants to get into Kubernetes to do that very easily. Policies like backup and restoration and networking policies, all these sort of policies and logic are reusable across different storage providers to make people's lives easier. And then also there's a testing effort where these tools and resources that Rook is defining in the framework here have a common testing effort from our integration testing, from the community, so you can leverage that to get into Kubernetes easier. So just last week, we started creating, we have up and running operators for CockroachDB and Minio as well, in addition to Ceph. And this is using that Rook framework where the coding job wasn't that hard anymore because we have these tools, we have these constructs to bring more types of storage into Kubernetes in a reliable, consistent way. There will be support for Nexenta as well soon too. All right, so let's take a little demo here real quick. So kind of put some of these things that we've been talking about together and show you what it looks like. So I think maybe make that a little bigger for the people in the back. Is that somewhat readable back there? Okay. Let's do the same here. Okay, so if we're over here in this window, I've just got a little watch going that's going to show us what we have running in the cluster. Namespaces, pods, services, persistent volume claims, things like that. We don't have much running right now. We just have the namespaces that come with the Kubernetes system I have up here running. That's it. So let's get a Ceph cluster running, and then we're also, on top of that Ceph cluster, we're going to run a stateful application, and I'll show you how easy this is. So let's go ahead and create. I'm going to use some aliases too. K is kubectl. I can only type so much. So it's two phases here. The first is that we need to get the operator itself running. So we deploy out a YAML manifest that describes the Ceph operator for Rook. And it goes ahead and declares some custom resources that we can see here as well, such as clusters, file system, object store, pools, things like that. And once the operator is up and running, which we should see over here, yeah, so we have the operator up and running. Once it's running now, we can do something like creating a cluster. So the custom type, a Ceph cluster that we've defined, we created an instance of it. The operator is watching. It gets that event that says, hey, the user wants a Ceph cluster. So the operator is going to go ahead and make that happen. I should be on this window here now, sorry. So what is the operator doing right now? It's very simple to say, oh, create a cluster, and okay, I will create a cluster for you. But there's more detail than that. So I don't know how much you all know about Ceph, but it has a number of components, such as monitors, OSDs, managers. And so what the operator is doing right now is that we asked it to use every node in the system, and what else did we ask? I think we could look at that in a second. But we've basically told it to create a cluster that can give me file storage, object storage, block storage, and the operator is acting on that on our behalf. So it's created a service you can see down here. It's created a number of pods for us. I may need to make this smaller. Yeah, we got to see some more services and things like that. All right, so then that's great. A Ceph cluster is running in Kubernetes. It's ready for holding data. That's only half the story. Let's actually use that data. That's actually the interesting part. So I'm going to do a couple of things here of defining a storage class. And that storage class is going to be able to, that's the link from a application that says, I want block storage, and then on the other side of that, for Rook fulfilling that storage request. All right, so let's go ahead and create WordPress and also MySQL underneath it. And let's watch over here as those start coming up. So WordPress is by itself, isn't a stateful app. It's just a front end, but it needs to store data somewhere in MySQL, and that's where it gets interesting, right? Where you can have blog posts, you can have comments, you can have all sorts of interesting state, right? So WordPress by its needs a backing store, a database, and that database needs to be stored or persisted somewhere. And so what we're seeing here is when MySQL gets created, it needs block storage. So it asks the Rook operator for a block device. And that goes through the process of creating a volume inside of the cluster and then attaching that volume to the correct node that MySQL is running on and mounting it and making sure that the MySQL pod is able to then start consuming it. So let's go ahead and look at WordPress real quick. All right, so we'll go to this address in a browser, and this should be a WordPress instance. Thank you. And I'm going to pick English, even though I've been trying to learn a little bit of Danish while I've been here. No, we're going to go even easier than that for me, or personalized, though, as well. Uh-oh, I think I clicked it too fast. Okay, and let's look at the different instances we have here. So we see that these persistent volume claims are representing the data needs of WordPress and of MySQL. So we can see that they both asked for 20 gigabytes, and those were bound and fulfilled by the Rook operator in order to make sure that that storage was available for WordPress. Here we go. So then so that's interesting, right? That we have a stateful application. It has data needs. Rook was able to not only create the underlying storage fabric, but also to provide usable block storage, file storage, whatever it is, for this app. So then one last thing to show you real quick is a bit of the management. So what I'm going to do here is I'm going to kill the database instance. So when we kill the database instance, because we're running in Kubernetes, we're going to get some very awesome management constructs here. So I killed it, and we should see MySQL terminating right here. And so when that database dies, all these Kubernetes amazing management capabilities we have here will bring up another MySQL instance, but that's not all that's happening here. What's also happening here is that the old MySQL instance had a block volume, and now it may be on an entirely different node. So the Rook operator and Rook agent will unmount and detach the volume from the old instance of MySQL and move it to somewhere else in the cluster, and where the new MySQL instance is going to come up and make sure it's remounted, reattached, so that the new MySQL instance, when it failed over, can continue using the same data. So if everything worked there, with the new MySQL instance running, we should be able to refresh and see the page here, and still be able to use the site. And the data is still there, even though the MySQL instance may be moving around the cluster. The data is going along with it, right? So we started from a blank Kubernetes cluster, brought up a storage system, brought up a stateful application using it, and we're seeing some of the management parts where the storage moves along with the applications. So I think let's go back to the slides real quick. And so, as I mentioned, we're an open source project. So we, we would love to have new contributors. We've got a nice, healthy community going, but we can always have more contributors. So one way to get involved is to come to our GitHub, contribute, open issues. If you use Rook and run into a problem, open an issue. Come talk to us on Slack. We actually have We actually have a conferences channel on our Slack right now, too, to keep in touch with each other as we're going through this. Rook_IO is our Twitter. We also have community meetings every couple of weeks. So we've got a community. We want to meet more people, talk to more people, and get more people interested in Rook. And this week, we actually have some more sessions as well. Since we are a CNCF project now, we have a Meet the Maintainers session tomorrow morning, Thursday. And then we have a deep dive into some more of the architecture of Rook that will be in the same room on Friday. And then I'm giving a talk about portability of data in Kubernetes on Friday in one of the bigger auditoriums. So we'd love to see you guys there too. And do we have any questions from anybody? Yes?
How is the state of support of Rook to AWS CDS?
The state of support as in support when there's a problem, or supporting those data types? Oh, okay. So the question was, what's the state of support for different data types comparable to what's in Amazon, like EBS? And so that depends on what the storage provider that Rook is deployed is. So when you deploy Ceph, you get file, you get block, you get object, and those are exactly comparable to EBS and to S3 and to whatever the name is of the shared file system in Amazon as well. So they're very comparable types of storage that are available in Amazon. Yes?
You were saying that Rook operator is not in the data path, so it can be down. And what about Rook agent? So will applications still work if we say Rook system itself is down, so Rook agent maybe, because it brings Ceph cluster, which runs in containers, I guess. Mm-hmm. So those containers may still be running when Rook is down, or?
Yeah, that's a good question. So the question is about what can be down in Rook for data to still be usable, for data to still be accessible. As we talked about, the operator is not on the data path, so that can be down. And the Rook agent part, as you noticed, that's only on the data setup path, so only at attaching and mounting time, and then also unmounting and detaching. That's the only time that the agent needs to be up and functional in order for things to go smoothly. But other than that, at steady state, while the distributed storage system is up and running, and reads and writes are coming in, the agent and the operator do not have to be up at all. Yes?
Yeah, for the Ceph backend, would you be able to support like a single node developer type of setup like MiniCube, for example?
Yeah, that's if you that may have been visible on the demo here. I was doing it on MiniCube, yeah. So MiniCube is entirely set up, and that's the common contributor workflow for Rook to do bug fixes and stuff. It uses MiniCube locally, yeah. Yes, in the back.
Hey, thanks for the presentation. Anyway, do you have any performance benchmarks, like a rough estimate of the number of PVCs that you could handle?
Oh, so that's a good question. So the performance benchmarking that we've done so far has been focused on read and write throughput and latency, things like that. I don't have any information about how many PVCs can be running or sort of the number of concurrent accessors to the data. I don't actually have a figure for that.
The read-write is fine. The critical part that you just mentioned, we were running on ClusterFS, but we had issues when we rebooted a node. The volumes could not be mounted or detached because ClusterFS was not there. So we are doing the same thing here in Rook, right? So more towards that, how the volumes could be attached or reattached when there is a node failure.
Sure.
Yeah.
Right. Yeah. And that's something that's really interesting. And we kind of tried to simulate that for you today of when something goes wrong, to move data around to another node in the cluster, or excuse me, not even the data itself. Because if you think about a distributed storage cluster, you've got all the data already spread around, and when one node goes down, you're losing some of the redundancy, the durability of the data is getting affected, but it should absolutely still be available even though you've lost the node. The interesting part for the immediate thing you have to worry about when you lose a node is more so any of the local applications or instances like pods that were using the data on that node, right? Yeah. And so as soon as the node is noticed to be lost, then the Rook agent starts doing work to, if it can, because God knows what might be wrong with the node, it may not be able to, it might be completely powered off, right? And it won't be able to unmount it or detach. But as soon as the node is lost in Kubernetes, it'll start doing that work and move the volume somewhere else as quickly as it can. And we've, with some of the tests that we've done in, for instance, in Google's compute engine, GKE, we've done that, and within 30 seconds or so, it shows up on another node, and that pod is already scheduled and using the data again on another node. So it's got a little bit of downtime to figure it out, but it's fairly minimal.
Thanks.
Hi. So quite recently faced an issue with Bluestore not releasing space in the data dir, even so I got a feeling it's kind of a known issue. Do you possibly have any more background to that?
The thing I remember about that, and Alex might remember more about that as well, but the Bluestore it's designed for devices, specifically running on raw devices. So running on an existing file system, you don't have good performance on that anyway, since you're going through multiple layers. But you also don't have that ongoing management of freeing blocks. And I don't know if that was a design flaw in it necessarily, but Bluestore is definitely intended to be used on raw devices. Do you have anything else to add to that, Alex?
Yeah, it's simply because I think it was the discard syscall or something. It wasn't passed through or not even triggered for Bluestore, and simply because of that, the file system is growing, is getting full. Yeah.
It's great. I mean, on this, it's great on a cloud. We have storage option. What about on premises? Let's say we VMware backed by SAN. So how does it work then?
Oh, is it on premise?
Yep.
Really well. Also, actually, excuse me, God, I need to drink water. So we're running a set of bare metal nodes in our office for quite a while, and deploying to the important part is having Kubernetes there. So once you have Kubernetes, that abstracts away the underlying environment. So it doesn't matter if it's a cloud provider or if it's an on-premise scenario, right? The storage cluster can be deployed, configured, and managed basically the same. It doesn't really realize that it's on-premise or in a cloud provider. So that's one of the interesting things about the power of abstractions, where the environment becomes much less prominent in the management of it because Kubernetes and other abstractions have kind of dealt with that for us. Time. I think we got one more minute here.
What would you say that is the biggest issue you're facing right now with Rook?
That's a really good question. I think, you know, so Rook is an alpha project right now. We're working on getting to beta. And the aspect of, you know, getting the management and, you know, edge case scenarios, you know, being able to deal with with failure, unexpected failures really gracefully. That's kind of the next, you know, that last part there of getting from an alpha project to a beta project. And those are the elusive ones that are difficult to track down, difficult to get reproducible and stuff to figure out what the root cause is. So I think those are those final issues about getting it to full and ready production reliability is the biggest, you know, thing that I'm concerned with personally right now, honestly. And that is the end of the session, I believe. So if you have more questions, you come talk to me. Thank you, guys.